propose implicit neural head synthesis via controllable local deformation field, which reconstructs detailed head avatars from monocular videos. Given the monocular video of a subject and segmentation masks, as well as expression, pose, and facial key points from a face tracker, we proposed a method to reconstruct a head avatar of the subject with deformable and controllable fine-scale facial features. With the trained avatar, we can control it by providing the model with new expression and poses from another source video. Previous methods have combined neural implicit methods with 3D parametric face models to represent personalized detail such as hair and accessories, as well as nonlinear deformations. However, none of the methods above is able to reconstruct fine details such as wrinkles around eyes and sharp mouth interior. We propose a pipeline that decomposes a backward deformation field into local fields centered at facial key points and use voxel grid to represent the canonical space, which provides higher capacity for details. To elaborate, we represent a face with neutral expression as a neural radiance field. We convert face pose into camera pose, cast rays in a deformed space accordingly, and sample on the rays. We learn an implicit deformation field that predicts the expression-dependent mapping from a point in a deformed space or face with expression and point in a canonical space or face with neutral expression. Implicit deformation fields proposed in previous dynamic NeRF methods use global MLPs to represent per-point rigid transformation or translation. We model face deformation as per-point translation as they are highly non-rigid. Global deformation field can be conditioned on expression codes to represent deformation due to expression, and additionally a per-frame deformation code to represent additional deformation. Instead of a global deformation field, we represent deformation as the sum of many local deformation fields centered around selected facial key points, and we use a subset of the facial landmarks from the face tracker as these key points. For each sampled point on the ray, we first convert it to the local space of each key point by subtracting the key point location and feed to the corresponding local deformation field. The final local deformation is the sum of the learned deformation and the key point deformation provided by the 3D mesh. We obtain the mapping between the deformed and canonical space through a weighted sum of all the local deformations based on the point's inverse distance to the key point. To save computation, we also use these weights to select the fields the points are fed into so that local fields with center too far from the point does not influence it. Similar to global field-based approaches, we condition each local field on a per-frame deformation code and an expression code. Using the same expression code for all the local fields is redundant. Hence, we apply a pre-computed attention mask on the expression code input to each local field. The attention mask masks out expression coefficients whose corresponding expression bases do not affect a particular key point location. For example, if we have an expression code with length 6 corresponding to 6 bases, at each key point, we can query the amount of deformation for each basis, normalize over all bases, and binarize to get an attention mask. In addition to the deformation fields, we represent canonical space as a voxel grid with TensorRF, which provides acceleration and further detail representation. We query local deformation fields and deform points from observed space to canonical space and query voxel grid to obtain radiance and density, which we accumulate using volumetric rendering to get the final pixel value. We train the model by comparing it with the ground truth pixel value. To better regularize the local deformation fields, we provide weak mesh prior by querying nearest point on the deformed 3D mesh and use its deformation as a point to guide the deformation field. To constrain the deformation field and preventing it from falling into local minima, we regularize the norm of the total deformation at each point by applying L2 regularization. Additionally, we propose local control laws to enforce sparsity of the local deformation fields. We use the fact that the same key point deformed by two different expression and pose should still be at the same point in the canonical space with neutral expression. Hence, at each iteration, we sample 2 frames and cast rays from each key point. We first query the pipeline to obtain the surface intersection of the rays corresponding to the key points in the deformed space. Then, we deform them to the canonical space and enforce two key point locations in the canonical space to be the same. We use L1 loss to minimize the effect of outliers. Let's see some more results. We showcase the results for reconstructing unseen expression and pose. As can be seen from the rendered images and depth maps, the detailed deformation learned is both in the texture and geometry. We can perform expression transfer from another subject to our trained head avatar. Lastly, we provide additional comparison with other state-of-the-art approaches to see our method can reconstruct better details. Thank you.